This is Professor Pelton. This is part 2 of chapter 3, section 5. Now we're going to focus on horizontal translations or horizontal shifts. So if I add or subtract on the insides of a grouping symbol, I'm going to shift left or right. Remember, it's counterintuitive. Add is left and minus is right. Anything that's in the inside of a grouping symbol is going to be counter to what you think it is, whether it's a translation or a stretching or shrinking, whatever you think it is, and reflections. Okay, so let's try a standard quadratic function. So if I have x squared, what's a quadratic? So let's make a simple table of values. So x squared will be, we'll just plug in values that are close to the origin. Okay, so if I square -2, I'm going to get 4. If I square 1, I get 1. Square 0, I get 0. Square 1, square 2. Okay, so this is the table of values for a basic quadratic, which is the parent of all of them, basically. So -2, 1, 2, 3, 4. -1, 1, 0, 0, 1, 1, and 2, 4. Okay, so that's essentially what a quadratic looks like. It's a parabola. Okay, we'll just choose another color here. So what if I -3 to the inside? What's I'm actually going to do is move it to the right 3, to the right 3, to the right 3, to the right 3. 1, 2, 3, 1, 2, 3. So I get a new parabola over here. That's to the right. Okay, so if you make a table of values, what you'll notice is none of the y's actually changed. I'm still at 4, 1, 0, and 4. Okay, what did change is the x values. They went over. So if I add 3 to each of these, what I'm going to get is 1. I'm going to get 2. I'm going to get 3. I'm going to get 4, essentially. Oh, I missed one. Put the 1 in there. So if I add, so that's going to move up 1. Right, because I added 3 to that. That gives me 4. And I add 3 to that. That's going to give me 5. Okay? And you can verify that on the graph. This is now a 5, 4 coordinate, essentially, right? And you can do a table of values or a graphing calculator to verify that result. All right, pause the video. Try the student problem for yourself. Okay, so we're going to do a standard square root function, which we've already done, right? We know that the square root of x, you can't put in negatives. So we're going to plug in positive numbers. We'll do ones that we can do easily. So we'll do 0, 1 actually is easier than 4, huh? I always forget the easiest one. 1, 4, 9, 16, so on and so forth. So we get 0, 1, 2, 3, and 4, right? Because obviously the square root of 16 is 4, so on and so forth. Okay, do they all fit in the graph? No, but we don't need to put every single one. So we have 0, 0, we have 1, 1, we have 1, 2, 3, 4, 2, and we have 9, 3, and the 16 doesn't fit on there, but that's absolutely fine. Okay, so what we're going to do now is do the +2, which actually subtracts 2 from the x value. Okay, so we're going to go left 2, we're going to go left 2, left 2, and left 2. So there's our new square root graph. Although I missed that last point there, right? So what you'll notice is the y values in the graph do not change. They are 0, 1, 2, 3, and 4. What's happening is I'm minusing 2 from the x value, so I get -2, -1, 2, 7, and 14 if I actually graph that one. Okay, so write a function g that has the following transformation. Translate 2 units to the left, 2 units to the left. So if I do that, that gives me f of x plus 2 will actually move me to the left, right? So I need to replace my x with x plus 2. So I'm going to do 2, I'm going to parentheses plus 1, right? Because I'm replacing x with x plus 2. And x plus 2 will move me to the left. So I'm going to put x plus 2 in the inside. So that gives me a new function, which we're now going to call what? We're calling it g. So g of x is the new function, which is 2x plus 5, right? Because we have the 2 times 2 plus 1 more is 5, essentially. All right, pause the video. Try the student problem for yourself. Okay, so this time we're going to move 4 units to the right. So that's h of x minus 4, because minusing 4 will move me to the right. So I'm going to replace my x in this function with the x minus 4, right? So I'm going to use to change the color right away so you can see it visually pretty nice. So I'm replacing x, right? Replacing this x with x minus 4. So my new function is going to be called p according to the problem. Just as long as you call it something different, that's all that really matters, because it's not the original function anymore, because we have done a transformation. So this will be x minus 3, absolute value of minus 2. Okay? All right, so that's horizontal. Let's try some reflections. So the first reflection we're going to do is reflecting about the x-axis, because essentially if you put a negative on the outside, then it changes all of the y values, which is why you go over the x-axis. So again, we'll start with a standard quadratic. So we'll do an xy table. Okay. All right, so this is what we're doing right here. So plug in -2, -1, 0, 1, 2, things that are close to the origin. So I get 4, 1, 0, 1, and 4. Right, square all those numbers, that's what you get. So 0, 0, 1, 1, 2, 1, 2, 3, 4, and -2, 4. Okay, there we go. All right, so if I put a negative on the outside, what's going to happen is I'm going to flip over the x-axis because I'm changing my y value. But if I'm already on the axis, I don't go anywhere, right? So this one goes to here, right? Because I went over the x-axis. This one goes to here. And then let's see here, 1, 2, 3, 4. This one goes to here, correct? And then likewise on the other side. So that is my new function right here. Okay, so what you notice is it's only affecting my y values. My x values stayed exactly the same. So I go to -4, -1, 0, -1, -4. Okay, because essentially if you rewrite this at the end of the day, it's y equals -x squared. So you just square the data first, and you do the negative second, so that just changes the y value essentially. Okay, pause the video, try the student problem for yourself. Okay, so now we have a cube root function. So we'll do a table of values, x and y, and I'll choose things that are easy. I'll choose -8, -1, 0, 1, and 8, because I can do the third root of -8, right? That gives me -2. The third root of 1 is 1. The third root of 0 is 0. This is 1, and this is 8, right? Because essentially 8 is 2, 2, 2. I'm sorry, why did I write 8? It's 2. I said 2, but I wrote 8. I don't know why I did that, right? Because the third root of 8 is 2, because it's the third root of 2 to the third power, right? So we know this. So that's why I didn't want to pick 2, 3, 4, 5, because those ones are decimals, not easy to graph. So 0, 0, 1, 1, -1. Oops, that's -1, right? And then 8, 2, and -8, -2. So we get the standard pinwheel, which is what a odd root looks like, right? So I do third root, fifth root, seventh root, ninth root. They all look the same, essentially. Okay, so without doing any work whatsoever, I know that this is going to change my y value. So I'm going to flip over the x-axis. So this one's going to go to here, right? This is going to go to here. The origin stays the same because it's already at the origin, right? This one's going to flip to the top, and this one is going to flip to the top. So essentially, this is my new function. It just goes the other direction, right? All right, so these arrows aren't really here. I'm just drawing those for visual sake, showing that I went over the x-axis. So my new table of values, x and y. My x don't change, right? I'm still at -8, -1, 0, 1, and 8. What happens is these flip to +2, +1, 0, -1, -8, essentially. And you can do out the math and or graph it to prove to yourself. All right, that is the end of part 2.